So we definitely want to measure both the stress and the strain. So here's our strain formula we had from the previous Prezi. Epsilon, or the strain, is simply the change in length relative to the original length, where you are now minus where you were before, relative to where you were before. That's going to allow us to calculate the strain. If we're along the major axis, the long axis, we're going to call that axial strain along the major axis. If we're on the minor axis, we're going to call that lateral strain. Anybody who has played football before, you know that if this is the field and you're running down the field, we don't call that an axial pass, but it could be called an axial pass inside engineering. But if you throw the football side to side, it's called a lateral pass, because you're throwing it along the short width of the field. So if that helps you remember which is which. So we can measure axial strain, we can measure lateral strain, just totally depends on which dimension is changing. So when it comes to tension, here's our picture of tension again. Here's our little device, and there's the force pulling it away from the top and pulling it away from the bottom. Here are the internal forces. Here's our necking down again. But if we go ahead and measure how long is it elongating, our axial strain, and if we measure how skinny it's getting, our necking down, our lateral strain, if we go ahead and ratio those things, we're always talking about ratios, if we compare how thin it's getting strain-wise to how long it's getting length-wise, that thing happens to have been coined by a previous engineer, and his last name was Poisson. He was French. Looks like it's spelled poison if we were here in the United States, but I believe it's pronounced Poisson. I'm not French, so I don't know. But this is a specific ratio from Professor Poisson, who said, hey, if we make this a thing and everybody sort of measures it the same way, we can go ahead and compare all kinds of materials, and we can talk about their Poisson's ratio. So again, the Poisson's ratio is simply the lateral strain relative to the axial strain. And quite honestly, usually the axial strain is much longer than the lateral strain. So this is usually, not all the time, usually a number that's less than 1. This is small compared to this guy being big. So we'll see what happens. Here's Poisson's ratio under compression. Same process again. We're going to push along the major axis. Here's the major axis. Here's the minor axis, or the lateral axis. We're going to ratio the lateral change relative to the axial change, and we're going to get another Poisson's ratio, but this is the Poisson's ratio, or the PR, for compression for different materials. Here's our good friend Simon Poisson, 1781 to 1840. He is from France, and again, he was a scientist slash engineer, and also a mathematician, who sort of standardized this idea of measuring materials and measuring their Poisson ratio and being able to tell who's strong and who's not so strong.